In this video, we're going to finish our example of a one standard deviation confidence interval using the chi-square distribution. What I've written here is basically a confidence interval, but it looks not quite right yet. It's almost a statement that is something kind of obvious. It's like saying, this is our test statistic. You'll remember that from our last formula, the last hypothesis test. The test statistic, which is a chi-square, which is distributed in a chi-square way, it's between a lower chi-square value and an upper chi-square value. And in a way that means, it's obvious because, yes, of course, we can put a number between any two other numbers. Well, when you make a confidence interval, you're giving a lower and upper bound to where you're likely to find the population parameter. So if I take this formula, which has a sigma squared in it, and bound it between two numbers, I am going to create, in a way, a confidence interval. But the problem is this middle stuff here, it's not just sigma squared. It's a sigma squared on the denominator, but then there's an extra s squared and an n minus 1. So I'm taking this obvious statement, that's in air quotes, and I'm trying to solve for sigma squared, because then I'll be able to say, hey, sigma squared is between these two numbers, and then that result is our confidence interval. So what I'm going to do first is I want to solve for sigma squared. So I need to get rid of this n minus 1 and s squared. So I'm going to divide each piece of this inequality. I'm going to divide it by n minus 1 s squared. Even the middle, divide by n minus 1 times s squared. And the last, divide by n minus 1 times s squared. So what's happening in the middle is all that cancels out, and now we have some more terms or more factors over here on the left and right side. So I have chi-square, I'm going to put L for lower, just to shorten this, n minus 1 times s squared. It's between, or actually it's less than 1 over sigma squared, which is less than chi-square upper, I'm going to just represent that with a u, divided by n minus 1 times s squared. All right, so I'm almost there. But this is not solved for sigma squared. I do not have plain old sigma squared in the middle. I have 1 over sigma squared. So I need to get a sigma squared up on the numerator. And the way I'm going to do that is I'm going to give you an analogy, and then we will do something similar with this chi-square interval. So let's have an analogy. 2 is less than 3, and 3 is less than 4. Well, you guys believe that. So if we took reciprocals of these and made this a 1/2 and a 1/3 and a 1/4 and tried to make an inequality out of it, 1/2 is actually bigger than 1/4. So I'd need to put 1/2 over here on the right side because that's the biggest. 1/4 is the smallest, and 1/3 is between 1/3 and, 1/3 is between 1/4 and 1/2. So the idea is that if you have an inequality, if you rotate where the endpoints are, but take reciprocals at the same time, you still have a true statement. So that's what I'm going to do over here. I'm going to take the reciprocal of all three pieces, but then I'm going to switch the order. So this one on the left goes over here, the one on the right goes over there, and the reciprocal of 1 over sigma squared will become plain old sigma squared. So the reciprocal just means flip, or put it in reverse order. So my fraction over here on the left side will be chi-square upper on the denominator, and then the numerator is n minus 1 times s squared. And then the left side, flip that, chi-square lowers on the denominator, and then n minus 1 times s squared is on the numerator. So doing those steps, we now have the confidence interval formula. Now, the textbook is probably not going to show you all these steps. But it's kind of fun that with this interval, you can solve for your parameter and you generate your confidence interval. And in a way, that's what happens with all the other confidence intervals we worked with as well. So what we need to know to build a confidence interval is we need to know our degrees of freedom, those go on both sides, our sample standard deviation squared, that goes on both sides, our sigma squared, that's what we're estimating, and then we need to know two chi-square values. And the way to remember this is the numerators are the same, but then the upper value goes on the left side and the lower value, the smaller number, goes on the right side. So they're opposite like that. And you can tell that when we were solving, that's why it got switched around like that. Okay, so let's figure out what we know. From the last problem, we had n equal to 25 people. We were looking at, I'll scroll up to this. We were looking at the lines and the variation among the waiting times. We were hoping to show that shorter waiting times were happening when we had one line instead of multiple lines. We had a standard deviation of the sample of 3.5 minutes. So I'm going to put this back over here. We had S was equal to 3.5. And in a confidence interval, we're trying to estimate sigma. So we're not going to use that 7.2 that we saw earlier. We're trying to estimate it. For a hypothesis test, you have to pick a value for sigma to compare against. But with an interval, you just are going to estimate what you think sigma might be, and there is no picking of sigma. So now we need to get chi-square values. We need to get a chi-square upper and a chi-square lower. So I'm going to draw a picture again just to show you what we're going to get these numbers from. So remember, chi-square is right skewed. The one thing different about this interval compared to z or t intervals is that you need to pick two unique chi-square values. It's not a plus minus. Remember with a z or t interval, it was x bar plus or minus z times sigma over the square root of n. Because the normal distribution was symmetric about 0, when you found your interval, there was a negative z value and there was a positive z value. They were just as far from the center on either side. But this chi-square distribution is not symmetric. So when you're finding your chi-square lower and your chi-square upper, if you put 95% in the middle versus, this 95, you're going to have two really different chi-square values. So we have to look at the table and pay attention to these little subscripts, the lower and the upper. If I put 95% in the middle, so just like we've done with other math, if there's 95% in the middle, that leaves 5% total in the tails. So that leaves 0.025 and 0.025 in each tail. So this chi-square lower and chi-square upper, the upper gets the 0.25 because it's area in the right tail. So the chi-square model, like we saw before, always gives us area in the right. So that means this chi-square lower, it's going to look a little funny. It's not a subscript of 0.025, it is area in the right. So when I highlight area in the right, here, let's use the highlighter. Area to the right, we're shading the 95% and the 2.5%. So in the end, we're going to end up with 0.95 plus 0.025, so we'll have 0.975. So where did I get that? I added the middle 95% plus the right tail 2.5%. So we'll look at our chi-square table and look for the 975 column and the 025 column with our degrees of freedom. Let's throw this in there. Degrees of freedom of 24. All right, so let's go to a chi-square table. So we said chi-square 0.975. That's here, this third column or the middle column. And I want 24 degrees of freedom. So 12.401. So I looked at my degrees of freedom. I looked at the area in the right, that was the 95% plus the 2.5%. And my lower critical value is 12.401. So let's make this obvious here, 12.401. Actually, let's pick a different color, make it more obvious. 12.401. Now let's go to the chi-square 0.025. Now, this table doesn't have the 0.25, so I need to go to the next page and then look for chi-square 0.025. Now, it's also in the middle column. It's kind of symmetric like that. If you use the far left column for one side, then you're going to use the far right column for the other side, and it kind of marches in towards the center, column by column. So 0.25, 24 degrees of freedom, 39.364. 39.364. Let's make that 4 look better. All right, so we have our two chi-square values. We have the upper and the lower, so we're ready to start constructing our confidence interval. All right, let's keep that interval formula just in our sights. So our goal is to estimate sigma squared. Now, I should actually say that this formula starts off with sigma squared, but maybe you don't want an interval for your variance. You want an interval for your standard deviation. At the very end, we're going to take a square root. So remember that relationship? Sigma squared is equal to the standard deviation squared. And if you take the square root of your variance, that's how you get your standard deviation. So I start off with an interval for a variance, take the square root later. All right, so we know the numerators are the same, and minus 1 times s squared. So that's 25 minus 1 times 3.5 squared. And the other numerator, 25 minus 1 times 3.5 squared. And then our lower and upper critical values. Now, the way that you can think about this is this interval, you have to have a small number on the left side and a big number on the right side. You know, your answers, because that's how an interval reads. It's lowest to greatest. So when I am putting in my critical values here, to get the smallest number, I have to have the biggest denominator because the numerators are the same. So putting the 39.364 in the denominator will, once I do my division, it'll give me the smallest answer compared to putting 12.401 on the right side. It's like saying when you have more people at a party, everyone gets a little less food. So you'd have a little less food on the left, and you'd get more food the fewer people you have over here on the right. All right, so to the calculator now. So when you are doing this by hand, you want to make sure that you use the correct order of operations. So I'd take 24 times 3.5 times 3.5. I'd get my answer, and then divide that by 39.364. So I get 7 let's go out to 2 decimal places, 47. Less than sigma squared, less than our next number. All right, so now we have 24 again, times 3.5 times 3.5, and then divide by 12.401. This time we'll get 23.71. So I'm just going to double check those real quick. All right, looks good. So this is an interval, a confidence interval for sigma squared. If I want to do a confidence interval for sigma, I'm going to take the square root of 7.47, put a sigma in the middle, and then take a square root of 23.71, and I'm going to actually do the math here. All right, so here we go. This is a confidence interval now for sigma. So remember, these were standard deviations of the wait time in line. Based on our sample of 3.5 minutes for a standard deviation, we can now interpret our interval. We are 95% confident that the standard deviation of wait times is between 2.73 minutes and 4.87 minutes. Oops, there we go. All right, so this is how we worked by hand. Let's go ahead and try this using Statcrunch, and I'll show you also how to use the chi-square calculator again. So back to Statcrunch. Last time we had done a hypothesis test. I'm going to go back to Stat. Actually, I'm just going to go back to my options and edit. This is the same thing as if I went to Stat and then variance stats, one sample with summary. If I click on that, I'll get to this exact same menu. Because I had already used this before, my sample variance was 3.5 squared, so I got 12.25. My sample size was 25, and I want to click the button confidence interval for sigma squared. Well, again, we can take a square root and then we'll get a confidence interval for sigma. And I'm going to use 95% confidence level just because I picked it. Push compute. And here we go. Here's our confidence interval results. The lower limit 7.47 and the upper limit 23.71, and that's just what we got. But remember, this is for a variance, and then read the directions in the problem. If you're trying to make a confidence interval for a standard deviation, take the square root of each of these limits. So it's always variance first, take a square root second, and then we get to our answer. If you wanted to find the critical values in a different way, we can go to Stat, Calculators, and then chi-square. Select the between because we want to put 95% area between. So I'm going to put my 95.95 right there. My degrees of freedom, so I had 25 people minus 1, so that's 24 people. And then push compute, and we'll get the two critical values, that 12.401 and actually a lot more decimal places, and then the 39.3641. So you can see how asymmetric this distribution is. Here's 2.5% area, here's 2.5% area, and it puts 95 in the middle. So because the chi-square distribution is not symmetric, your two values, the lower and the upper, will not be the same. So there you go, how to make a confidence interval for a standard deviation or a variance if you want to. We worked by hand, and then we also worked via Statcrunch.